This is Dr. Beck, and this video is on solution formation and molarity. Before you begin this video, it's very helpful if you know a couple of things, including the previous information about intermolecular forces. There's a video on that. And if you're familiar with Gibbs free energy, that's helpful, and will help explain some of the energies that we'll get into in just a minute. At the end of this video, you should be able to do a few things. First, you should be able to describe the energy solution formation, describe the mechanism by which that happens, and be able to explain, for instance, on the AP test, what is required to have an ionic compound dissolved in into an aqueous solution. Secondly, you should be able to determine the molarity of solutions and perform dilution calculations, probably the most common calculation that's done in the laboratory. So a very practical skill to have. Okay, so this is about solutions. Solutions we're going to define as a homogeneous mixture of two or more substances. So meaning no matter where I look inside my container, I'm going to find the same ratio of those two. It will be equally distributed throughout the entire container. And all sorts of examples of this. So air is considered a solution, right? I have two gases or two or more gases that are mixing together, and wherever I look, I'm going to find the same ratio of hydrogen, oxygen, nitrogen, carbon dioxide, all floating around in the air. If I have steel, which is infused with hydrogen gas, so if I have a solid and a gas, they can make a solution as well. It makes the steel very brittle. Steel itself is a combination of iron and carbon, and those two solids can mix together, and that would be a solution. And one of my favorite examples, so soda pop, of course, is a solution. So lots of stuff in there. Is the sugar that's dissolved. It has salts that are dissolved, slightly different process, and also has carbon dioxide that's hidden away on the inside in the form of carbonic acid. The most common solutions that we're going to be using are aqueous solutions. These are really handy in chemistry because it's handy to do solution chemistry. Things will interact and mix with each other, and we'll get nice reactions that form. Okay, so we want to make a solution. Let's think about what this looks like. So I can take some salt, an ionic solid, and put it into solution, or put it into water, and this goes into solution. So just this dissolvation or the solvation of my salt, my ionic salt in this case. And I have a solution. Everywhere I look, I'm going to find about the same ratio of water and salt. You should have noticed a couple of things from this. So one is that I started with a nice structured ionic solid, so that's got to come apart. And the second thing you should notice is that this happened by itself. It was a spontaneous process. So there are three things that need to happen. So 3 steps for us to take a solid and dissolve that into an aqueous solution. So first we need to break the ionic bonds of the solid, right? So we call this lattice energy. How much energy does it take to separate two ions until they're infinitely far apart? But the energy required to break apart that ionic structure. So it's a very strong structure. We have to break our water-water bonds, and in fact we have to form water-ion bonds. So what does this look like? So remember, our water is bonded together quite strongly as well, and our ionic solid is bonded quite strongly together. So we have to break those. So there's 3 things that happen all at once. Here's an example of the water-water bonds that form. Remember our hydrogen bonding, this occurring between the hydrogen and the oxygen on an adjacent water molecule. And this bonding is quite strong and arranges itself into this nice ordered structure. And the third thing and last thing that happens, so we break our hydrogen bonds in our water, we break our ionic bonds of our solid, and lastly, it will form bonds between the water molecules and the ionic compound. Right. And we're going to have these interactions that form. So it costs energy. It's going to cost us energy to break those water-water bonds. It's going to cost us energy to break the bonds between ionic solid. And we get energy back when water associates with, in this case, the sodium ion. And so I have my negatively charged, my polar water molecule interacting with my ion. So this is not hydrogen bonding. This is just a polar ion interaction. There are some solutions that we can form where it costs more energy to break the lattice apart of the ionic solid and to break apart the water bonds than you get back when you form those water bonds with the ionic compound. Right, so this would be this dissolution, or putting things into solution would be an endothermic process. So energy goes into that process, right? Nevertheless, it's spontaneous. You may recall in Gibbs free energies, there are 2 energies that contribute to something being spontaneous. So we have the enthalpy, roughly heat, of the reaction, and entropy. And think for a minute just what's happening here. So I take my salt and I add in some solid salt, and I have a very solid, structured, with very few degrees of freedom in my ionic solid, and I have something that is crazily free, moving all over the place. I have lots of different arrangements they can have, so my entropy is going to be very high. I have a huge increase in entropy. So these solutions, these dissolving processes will be spontaneous processes because our enthalpy may or may be exothermic or endothermic, right? But we get some energy back from formation of water bonds, and we have a big increase in entropy. You may also recall from this equation about Gibbs free energy that temperature has an effect. And this shows up in a couple of ways. So at higher temperatures, oftentimes it's easier to get more salt in. So energetically it's going to be more favorable, and we'll be able to have a higher concentration or more salt. One way of representing this is in this solubility curve. So we have solubility, in this case written in terms of grams per 100 grams of water, and this temperature increase. And as temperature increases, most salts will be able to dissolve a larger amount of salt in the water. Potassium nitrate has a huge increase in the amount of salt that can be held in the water as temperature increases. You may also notice here that this is not always the case. So cerulean sulfate, as the temperature increases, the solubility decreases. Okay, so energetically it's often favorable for something to be dissolved in water, and what we want to do is come up with a way of describing this. So you may know that our oceans contain salt and contain a certain percentage of salt. So our oceans are about 3.5% salt containing. Human urine is able to contain about 2% salt. And for this reason, if you go and happen to be stranded on a boat in the ocean far away from everything else, that it is dangerous to drink a lot of seawater because you end up taking in more salt than your body is able to get rid of, and you will become essentially dehydrated by drinking too much water. This is one way of representing how much salt is present in water. So we can define this as a mass percent. Right? In this case, I said salt water is about 3.5% by mass. That means if I have a kilogram of salt water, that I have maybe 35 grams of salt that are present in there. So mass percent. It's not a really convenient way for chemists to describe things. It's a convenient way for us to measure things and for us to make solutions, but it's not a convenient way for a chemist to describe things. So usually in chemistry, we're concerned with sticking atoms together and how things are working on the molecular level. So we want to be working with atoms, molecules, or moles of things to be able to mix them together. So we want to know a solution. We want to know how much stuff is there. How much it weighs is not really important to us. So we need a better measure, and this is the measure that we're going to come up with is molarity, probably the most common measurement of describing how concentrated something is. In our definition of molarity, we're going to define this as describing a solution where we have the moles of solute divided by the liters of solution, or moles per liter. So let's take an example. So we can take our 3.5% sodium chloride that we find in seawater and figure out what is the molarity of that seawater. To make things easy, I'm going to take 1 liter of this, and that's going to be equal to 1 kilogram. So 3.5% of 1,000 grams is going to end up being 35 grams. Again, I want to get molarity, so molarity is going to be moles per liter. So I want to convert my grams of sodium chloride in that 1 liter into moles. It has a molecular weight of 58.44 grams in 1 mole. I end up having in those 35 grams the equivalent of 0.6 moles of sodium chloride. Lastly, I want to calculate molarity, and this is going to be equal to moles per liter. And this is going to be equal to my 0.6 moles that I've calculated divided by the 1 liter that I started with. And I have a molarity equal to 0.60 molar. This is a description that chemists can use to describe how many molecules are there, and we can use this in our chemical equation and chemical formulas to be able to predict reactions. Okay, I've described briefly how to calculate molarity. I suggest that you stop this video and try a few of these problems yourself. Here are some that will give you some practice. The answers are given here. If you're able to identify the correct answer, you're in good shape. Okay, probably the most common thing that we do in chemistry is we have a solution and it's not quite at the right molarity, so we need to change it. So we need to dilute it from something that's more concentrated into something that's the exact concentration that we need. When I worked in the lab, this was the most common thing that I did, was to take solutions that existed and make them more dilute so I could put them into reactions. By far the most common thing that I did, especially when I worked in the molecular biology lab. The principle behind this is that when we dilute something, the number of solute particles does not change, or in other words, the number of moles of solute are unchanged in dilution. So we start with our molarity. Molarity equals moles per volume. Then we can rearrange this, multiply both sides by volume, to say that the moles times the volumes that we start with, the molarity times the volume that we start with, is equal to the moles of solute. And this will equal the moles of solute that we end with, or M1V1 equals M2V2. Okay, let's do an example. So I want to make a solution that's going to be 5 molar. I want to end up with 3 liters of this. I have a stock solution. It's 12 molar hydrochloric acid. So how much water and how much concentrated hydrochloric acid do I need to mix together to make this solution? So I'm going to set this up so I have the molarity times the volume that I end with, 3 liters times 5 molar hydrochloric acid. It's going to equal the molarity times the volume that I start with, which is some volume of HCl, X, times my 12.0 molar. And when I calculate this, when I put it in my calculator, I discover that it comes to 0.80 liters of hydrochloric acid. And I want to bring that solution up to 3 liters, so the difference is going to be the amount of water that I add. So I'm going to add 0.8 liters of hydrochloric acid and 2.2 liters of water to that solution. Okay, here are a couple of dilution problems, one involving deranged molecular biologists. I think I knew them. And you can try these, see if you get the right answer. And if you have, you're in good shape. Okay, can you now describe the energy involved in dissolving a solution? What are the 3 things that need to happen? And explain why this is a spontaneous process, even if it's endothermic. Can you calculate molarity of solution? You'll need to do that a lot. And can you calculate dilutions of a solution? And I promise you, if you come anywhere near a lab, you'll be doing dilutions all the time. I hope you can do this. Thank you for watching.